Hi, I'm Samuel Bell, and today I'm really happy to be talking about our paper, Simplicity Bias Leads to Amplified Performance Disparities. So there are three motivating questions for this work. The first is that we're interested in which parts of the data a model will find difficult, and whether or not we can identify that ahead of time. The second is whether the concept of data difficulty varies between models. In other words, is data difficulty model specific? And the third question is, if you accept that data difficulty is model specific, what if data difficulty aligns with demographic information? Crucially, for point number 3, this isn't something that's intrinsic or innate about different demographic groups, but we're interested in the model's view of the data. What if a model finds one group harder than another? For a little bit of background, there is converging evidence that certain models have a preference for simple, i.e. they have a simplicity bias. This means they tend to learn simple functions before more complex ones. And it also means they tend to rely on lazy shortcuts instead of learning what we'd intended them to. What we're interested in is how this notion of simplicity bias might interact with a model perceived complexity difference between groups. So when a model finds one group complex and another simple, does simplicity bias come into play? Just to give you a concrete example, let's take a look at this example data distribution on the left, where we have a binary classification task of solid triangles versus hollow circles, on the left versus the right. But we also have group annotations indicated here by the background color. The blue background represents a more simple group with an easily linearly separable decision boundary marked in white. Against the red background, we imagine a more complex group with a non-linear decision boundary. Now, just to reiterate, we aren't saying that this kind of distribution represents something fundamental or intrinsic about different groups, but instead you could imagine it as a function of data quality, pre-processing choices, or even something like pre-trained embedding quality, each of which are known already to vary along lines such as geography. In our work, we first train one model on each group separately. So we train a model on just the blue group, and we train a model on just the red group. And we might get test accuracy curves that look something like these dashed lines, where the blue group ends up with higher test accuracy than the red group. We call this gap during single group training estimated difficulty disparity, here marked D tilde. Before we move forward, I'd just like to note we've chosen to operationalize the concept of difficulty via test accuracy, but we could easily choose a different evaluation metric. Subsequently, we then train a model on both groups together. This is conventional training that you're probably familiar with. And we also see a performance disparity here, which we call observed difficulty disparity, here denoted D. At this point, we've presented the model with a choice of which group to prioritize. To achieve an increased accuracy averaged over the whole set, it could choose to prioritize the simple group, the complex group, or both groups. If the model chooses to prioritize the simple group at the expense of the complex group, we see an increased observed disparity relative to what we might have estimated from single group training. When we see observed difficulty disparity greater than estimated, we call this difficulty amplification and link it directly to simplicity bias. To test this out for real, let us turn to our key experiment designed to isolate difficulty amplification in a controlled experiment. Here, our data is group balanced, i.e. both groups have the same number of samples, and there are no correlations between group and label. So the model can't leverage what it knows about group to infer anything about labels. The experiment follows the same setup as before, with the simple and complex groups on blue and red. But in our experiment, we stitched together CFAR 100 classes in order to create an artificial delineation between a simple group and a complex group. On the top, you see aquatic mammals versus flowers. They're very easy to separate. Whereas on the bottom, you see two different types of mammal that are very hard to separate. The precise classes chosen are based on the actual test accuracies of a ResNet 18 model. They aren't based on our human intuition. If we were to train models on this task, we would expect to see that the easier group outperforms the more complex group in terms of test accuracy. And this is exactly what we see in the central figure, here marked by the solid lines. But we're more interested in the gap between the two lines, i.e. the observed difficulty disparity, here marked as the black solid line in the rightmost figure. Observed difficulty disparity peaks early in training before decreasing to a plateau around 0.2. Most importantly, this observed disparity is above the dashed line, which is estimated disparity. So in this case, what we're seeing is that the model does indeed find one group more simple, but then it doubles down. This is evidence of difficulty amplification, a direct result of simplicity bias, in a controlled experiment where this cannot be attributed to a majority-minority group imbalance or to spurious correlations between group and label. Subsequently, we can repeat the experiment by drawing many different versions of this task from CFAR 100, such that we can plot observed difficulty disparity as a function of estimated difficulty disparity for various models. Here on the left, in the blue line, we have a lower performing model, Levent, which tends to attenuate difficulty disparity. And in the orange, we have ResNet 18, which tends to amplify. We call the slope of this line amplification factor, or K. We can repeat this over many models, and we see a figure that looks something like this, where if one is selecting models based on overall accuracy over the test set, the models we would tend to choose are those which amplify difficulty disparity. The most important point to take away from this figure is not which models amplify, but that model choice matters, and that the performance disparities are not solely a function of the data. We also evaluate the effect of other design decisions. Just to highlight two here, on the left, we look at network width in a ResNet 18 in order to evaluate the effect of parameter count or network capacity, finding that increased width tends to decrease amplification. This is interesting in light of previous work suggesting that overparameterization tends to increase a reliance on spurious correlations. On the right, we have the effect of training time. We can see that amplification factor peaks early during training before decreasing to a plateau just above 1. We interpret this as evidence that seemingly innocuous design decisions, such as whether to use a common regularization strategy, early stopping, might indeed be harmful and further amplify performance disparities. To turn from our synthetic task to a real-world dataset, we present two practical case studies. First, for demonstration purposes only, we train an age classification model on the FairFace dataset, disaggregated by race annotation. While FairFace is already a reasonably balanced dataset, we explicitly rebalance it using subsampling to exactly match the numbers of samples and the distribution of ages across groups. So once again, there is no way to use information about race annotation to learn anything about age. We present much more extensive results in the paper, but just for a snapshot, they look something like this. This figure is the performance disparity of samples annotated as Black versus samples annotated as East Asian. A positive value on the y-axis indicates higher performance for the group annotated as East Asian versus the group annotated as Black. Comparing the translucent bar to the opaque, or estimated difficulty disparity to observed, we see higher observed difficulty disparity than estimated, indicating difficulty amplification in practice. For a second, very brief example, following the same format as before, we also present results from a multi-label object classification task on DollarStreet, disaggregated by household income. Here, a positive value on the y-axis implies higher performance for samples in the top household income relative to the lowest income quartile. Once again, comparing translucent to opaque, we see higher observed disparity than estimated, i.e. evidence of difficulty amplification on a real-world dataset once again. Just to draw a couple of conclusions before wrapping up, the most important point to take from this work is that performance disparities can emerge even when you have fully balanced groups and in the absence of spurious correlations between group and label. So it's not just enough to fix one's dataset, something we have a lot more to say about in the paper itself. Our second main conclusion is to suggest that commonly used models, such as those selected according to high overall test accuracy, further amplify performance disparities because they over-prioritize the groups they find simple. The amplification factor itself is model-specific and varies by both architecture and various design decisions. We highlight that difficulty disparity and difficulty amplification are both evidence of the complex interplay between data, model, and optimization, and argue that investigating any one of these aspects without the others is likely to be an incomplete account. Through our case studies on FairFace and DollarStreet, we also demonstrate that this complex interplay has practical, real-world impact that manifests through disparities along the lines of both race and household income, respectively, in our case studies. With that, I'd like to say thank you once again for listening. And if you're attending FACT in person, please do come find us on Monday, June 12th, 3:15 p.m. CST in room W196A for paper session 2. If not, please do feel free to send us an email, and you can see our contact information above. Thank you again.